On the 18th of December, 2021, a rocket lifted off from the Guiana Space Center on the northeastern coast of South America and climbed into the sky carrying the most expensive, most complex, most carefully engineered scientific instrument that human civilization has ever placed beyond Earth's atmosphere: the James Webb Space Telescope. 25 years in development. $10 billion in cost, a mere 6.5 meters across, composed of 18 hexagonal gold-plated beryllium segments that folded for launch and deployed in space like the petals of an impossible flower. A sun shield the size of a tennis court, composed of 5 layers of a material thinner than a human hair, designed to keep the telescope cold enough, just 40 degrees above absolute zero, to detect the faintest infrared light in the universe. The engineers who built it, the scientists who designed it, the astronomers who had been waiting for it for a generation, they knew it would be transformative. They knew it would see further and more clearly than anything before it. They knew it would change our understanding of the universe in ways they could not fully predict. They did not know it would find something that, by everything we thought we understood about how the universe works, should not be there. Let me tell you what James Webb found, and then let me explain why it is not merely surprising or unexpected, but genuinely, deeply, structurally disturbing, in the way that the best discoveries in science are disturbing, because they do not just add to what we know, but challenge the foundation on which everything we know is built. Begin with the Standard Model, not the Standard Model of particle physics. That is a different story, though one equally full of tension at its edges. The Standard Model of cosmology, the framework that describes the large-scale structure and evolution of the universe from the first fractions of a second after the Big Bang to the present day. Its technical name is lambda CDM, where lambda refers to the cosmological constant, Einstein's term for the dark energy that drives the accelerating expansion of the universe. And CDM stands for cold dark matter, the invisible. Gravity-producing substance that makes up roughly 27% of the universe's mass energy content. This model is extraordinarily successful. It predicted the large-scale structure of the universe, the cosmic web of filaments and voids and galaxy clusters with remarkable accuracy. It predicted the pattern of temperature fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space with a precision that is almost miraculous. It predicted the abundances of hydrogen and helium and lithium produced in the first few minutes after the Big Bang. It has survived decades of increasingly precise observational tests and emerged stronger after each one. It is our best description of how the universe evolved from its earliest moments to the present. And it makes specific, testable predictions about when the first galaxies formed, how large they were, how much mass they contained, how quickly stars could have assembled inside them. Those predictions are what James Webb is testing. And some of what it is finding does not match. In July of 2022, the first science images from James Webb were released to the public. They were extraordinary in every sense. The deepest infrared images ever taken, fields of galaxies at distances and redshifts that had never been reached before, light that had traveled for billions of years to reach the telescope's detectors. The universe in its earliest, most distant, most pristine state. And almost immediately, the astronomers began to find things that made them pause. Galaxies, bright, massive, well-formed galaxies. Galaxies that by their redshift, by the degree to which the expansion of the universe had stretched the wavelength of their light, existed when the universe was only a few 100 million years old. When the universe was less than 5% of its current age. When, according to our models, there simply had not been enough time for structures of that size and mass to have assembled. Let me explain why this matters. In the lambda CDM model, structure forms through a process called hierarchical assembly. Small things form first. In the earliest universe, quantum fluctuations in the density of matter, tiny variations in how densely matter was distributed. Variations so small they left their imprint in the cosmic microwave background as temperature fluctuations of a few parts in 100,000 began to grow under gravity. Dense regions attracted more matter from their surroundings. They collapsed and formed the first stars, which were enormous by the standards of stars today, hundreds of times the mass of our sun, blazing with an intensity that burned through their fuel in 1 million years and died in catastrophic explosions. These first stars enriched the surrounding gas with heavier elements. New generations of stars formed in small clumps of gas and dark matter called halos. These halos merge with each other under gravity, combining their stars and gas into larger and larger structures. Over hundreds of millions of years, the first true galaxies assembled small, irregular, actively forming stars at a prodigious rate. Only much later, over billions of years of mergers and accretion, did large, massive, well-organized galaxies like our own Milky Way assemble into their present form. This is what the model predicts. Structure builds up gradually. The early universe should contain small, irregular, actively forming galaxies. Large, massive, well-organized galaxies should be rare or absent in the first billion years. James Webb is finding the opposite. Among the most startling early results were what astronomers began calling, in their papers and at their conferences, the impossible galaxies. Galaxies with stellar masses, with total masses of stars, comparable to our own Milky Way or even larger, existing when the universe was only 300 to 500 million years old. Galaxies that are not small and irregular, but large and bright, and apparently well organized. Galaxies that should not, by any reasonable reading of our standard model, have had enough time to accumulate that much stellar mass. One paper, published in the journal Nature in early 2023, described 6 candidate galaxies at redshifts between 7 and 10, meaning they existed when the universe was between 500 and 800 million years old, with stellar masses so large that the lead author, Ivo Labb of Swinburne University in Australia, said publicly that when he first saw the data, he assumed there was a mistake. He checked the analysis multiple times. He had colleagues check it independently. The result held. He described these galaxies as looking like fully formed adult humans in what should have been a nursery of infants. The phrase stuck, because that is exactly what the tension is. The universe at an age of 500 million years should look like a nursery, small, messy, early-stage galaxies in the process of assembly. What James Webb is finding, in at least some cases, looks more like a gallery of finished work. How much stellar mass are we talking about? The numbers in Labb's paper were startling. Some of these candidate galaxies appear to contain as much as 100 billion solar masses of stars, roughly comparable to the total stellar mass of the Milky Way today, packed into a universe that was barely a few percent of its current age. In the lambda CDM model, forming that much stellar mass in that amount of time requires star formation rates far in excess of anything the model predicts for early galaxies. It requires converting gas into stars with an efficiency that approaches 100%, turning essentially all the available gas into stars with almost no waste, which is not physically plausible by any mechanism we currently understand. Stars form inefficiently. Feedback processes, the radiation and stellar winds and supernova explosions from newly formed stars, heat and expel the surrounding gas, shutting down star formation before all the available fuel is consumed. The efficiency of star formation is typically a few percent, not 100. To form these galaxies in the available time, you would need either implausibly efficient star formation, or you would need to start with more mass available at earlier times than the Standard Model predicts. Or you would need some mechanism for assembling mass faster than hierarchical merging allows. None of these options fit comfortably within the standard framework. I want to be precise about what this means and what it does not mean, because the history of science contains many examples of anomalies that turned out to have mundane explanations, and I do not want to overstate the case. Some astronomers have proposed that the mass estimates for these early galaxies may be systematically high. Estimating the stellar mass of a distant galaxy from its infrared brightness requires assumptions about the ages and compositions of its stars, and those assumptions may be wrong in ways that inflate the apparent mass. Some of the candidate galaxies may turn out, on closer inspection and with better spectroscopic data, to be less massive than initially estimated. James Webb is now taking spectra, detailed measurements of the light at individual wavelengths, that will allow much more precise determinations of redshift and stellar content than the photometric estimates that generated the initial results. Some of the early candidate galaxies have already been confirmed at their estimated redshifts. Others have been revised. The picture is still developing. But here is what is significant and why the physics community is not dismissing this as a minor calibration issue. Even after accounting for possible systematic errors, even after applying conservative corrections to the mass estimates, a statistically significant number of early massive galaxies appear to remain. The anomaly does not entirely go away when you sharpen the analysis. It may shrink, but it persists. And it is not alone. The early universe anomalies from James Webb arrive alongside another tension in cosmology that has been building for a decade, and that James Webb's observations are not resolving, but deepening. The Hubble tension. The Hubble constant is the rate at which the universe is expanding, the relationship between the distance to a galaxy and the speed at which it appears to be receding. It is one of the most fundamental numbers in cosmology. And it can be measured in two completely independent ways. The first way works forward from the early universe. You take the detailed pattern of temperature fluctuations in the cosmic microwave background, data that is exquisitely precise, measured by satellites to an accuracy better than 1%, and you fit the lambda CDM model to it. The model is extraordinarily sensitive to the Hubble constant, and the CMB measurements give a value of approximately 67 kilometers per second per megaparsec. The second way works backward from the local universe. You use a chain of distance measurements, starting with parallax measurements of nearby stars, extending to Cepheid variable stars in nearby galaxies, extending further with type 1 supernovae used as standard candles to measure distances and recession speeds directly. This gives a value of approximately 73 kilometers per second per megaparsec, 67 versus 73. The difference is about 9%, and the statistical significance of the discrepancy accounting for the measurement uncertainties in both methods is now above 5 sigma. The threshold that physicists use for claiming a discovery. The probability that both measurements are correct and the discrepancy is a statistical fluke is less than 1 in 3 million. Both measurements have been checked and rechecked. Both have been refined with additional data. The discrepancy has not gone away. It has gotten larger as the measurements have gotten more precise. This means one of three things. Either the early universe measurement is wrong, there is some systematic error in how we extract the Hubble constant from the CMB, or the local measurement is wrong, there is some systematic error in the distance ladder, or the model is wrong, the lambda CDM framework is missing something that causes the universe to expand differently at different epochs than the model predicts. The third option is the one that keeps cosmologists up at night. because the lambda CDM model is not a rough sketch. It is a precisely calibrated framework that has successfully predicted a vast range of observations. Finding that it is wrong in a fundamental way, that something is missing from it, some component of the universe that we have not accounted for, would be the largest revision to our understanding of cosmology since the discovery of dark energy in 1998. And James Webb is not resolving the Hubble tension. It is, in some analyses, deepening it. Because if the early universe contains more massive galaxies than the model predicts, that could imply that the expansion history of the universe is different from what the standard model describes. That the universe expanded faster in its early stages than lambda CDM predicts, or that the density of matter at early times was higher, or that dark energy is not a simple cosmological constant, but something that evolves with time. All these possibilities are, in different ways, revolutionary. They all require changes to the framework that has been our best description of the universe for 20 years. There is one more thing that James Webb has found that I want to bring into this. Something that the telescope was not specifically designed to find, but that has emerged from its observations with a quiet persistence that the community is beginning to take seriously. Quasars, supermassive black holes at the centers of galaxies, billions of times the mass of our sun, accreting matter at furious rates and pouring out enormous quantities of radiation. We have known about quasars since the 1960s, and we have known for decades that the most distant quasars, those that existed in the first billion years of the universe, contain black holes that are already billions of solar masses in size. This has always been difficult to explain. How do you grow a black hole to 1 billion solar masses in less than 1 billion years? Starting from the black holes left behind by the first generation of stars, which were at most a few hundred solar masses, the timescale problem for early massive black holes is significant even in the standard framework, and various solutions, sustained super Eddington accretion, direct collapse of gas clouds into massive black holes, or starting seeds, have been proposed. James Webb is now finding quasars and the galaxies that host them at even earlier times and in even greater numbers than expected. The black hole problem is not getting easier, it is getting harder. Which brings me to the place where I always end up when I look carefully at the most challenging observations in contemporary cosmology. The lambda CDM model is not wrong in the way that a bad model is wrong. It is not producing predictions that are widely inconsistent with what we see. The vast majority of what we observe fits the model remarkably well. The cosmic microwave background, the abundance of light elements, the large-scale distribution of galaxies, the existence and properties of dark energy. All of this fits. But the anomalies are real. The Hubble tension is real. The early massive galaxies are real. The early massive black holes are real. They are not going away as the data improves. And a model that is mostly right but has persistent, statistically significant tensions with observations at its edges is telling us something. It is telling us that something is missing, that the framework is incomplete, that there is a room in the house of cosmology that has not yet been opened. What is in that room? We do not know. The possibilities range from modest revisions, adjustments to how we model dark energy, or how we model the efficiency of early star formation, to radical ones. Modified gravity, new species of dark matter, early dark energy that was more prominent in the first million years, physics at the inflationary epoch that differs from what we assumed. Each of these possibilities changes the picture in ways that ripple through the entire framework, and none of them has yet been confirmed. The James Webb Space Telescope was built to answer questions, and it is answering them in exquisite detail with extraordinary clarity, at distances and epochs that were simply beyond reach before. But in answering the questions it was built to address, it has revealed that the questions run deeper than we thought. That the universe at its earliest epochs behaves in ways that do not quite match the model that has been our best guide for 20 years. This is not a failure of science. It is science at its most alive. The instruments are working perfectly. The data is real. The anomalies are real. And the framework that has served us so well is now telling us quietly and persistently that it needs to be revised. Something is out there in the early universe that our models did not predict and do not yet explain. Something large, something bright. Something that formed faster than the physics we know says it should have been possible to form. James Webb is showing it to us. Now we have to figure out what it means. And that work, the work of understanding what the telescope has found, of revising our framework to accommodate it, of finding the new physics that accounts for what the data shows, is just beginning. The universe has been waiting 13 billion years to be understood. It is not going to make it easy.